In process applications, the operator must be able to assume control of any final control element and specify its opening. This video examines the mechanisms for providing this capability. In most loops, the operator specifies the opening of the final control element by switching the controller to manual and specifying its output. For the off-gas process, this works well for the scrubber duct inlet temperature loop only. Suppose the process operator wants the hot air damper to baghouse inlet to be 50% open. Can this be done via the baghouse inlet temperature controller? Not easily. The controller output is the difference in the hot air damper openings. Switch the baghouse inlet temperature controller to manual. Then change the controller output to 30%. The openings of both hot air dampers change. We could change the controller output until the hot air damper to baghouse inlet is 50% open, but this is inconvenient. Process operators prefer to explicitly specify the opening of a final control element. As PV tracking is disabled, the set point remains at 70 degrees Celsius. To return the process to its original conditions, switch the controller to auto. Some control systems collect the various functions pertaining to a final control element into what we shall call a valve block. One such function is the fail-open versus fail-closed nature of the final control element. Another function is to permit the operator to assume manual control at the valve block. Such valve blocks have two operational modes. We shall refer to these as remote and local. In remote, the valve block accepts the output value from a control block. In local, the valve block accepts the output value from the process operator. In both cases, the output value is specified in engineering units of percent open. Suppose we desire that the hot air damper to baghouse inlet be 50% open. Switch the valve block for the hot air damper to local. Then specify an opening of 50%. The damper is immediately driven to this opening. Switch the valve block to remote, and the control calculations resume. To specify the opening of the fuel gas valve, we could switch the scrubber duct inlet temperature controller to manual and specify its output. Alternatively, we could switch the valve block for the fuel gas valve to local and specify the opening. Doing the latter permits the same approach to be used for all final control elements. Switch the valve block for the fuel gas valve to local. Then specify a value of 87% for the valve opening. Observe that the output of the scrubber duct inlet temperature controller also changes to 87%. The scrubber duct inlet temperature is now above its set point. With the controller in auto, one would expect the controller to be reducing its output. However, this does not occur. To achieve this behavior, the scrubber duct inlet temperature controller must be tracking. This is the subject of the next video. Return the fuel gas valve to remote. The control calculations resume. Switching the fuel gas valve to local has consequences only on the scrubber duct inlet temperature controller. Tracking addresses these consequences. However, additional consequences are possible. Switch the fresh air damper to local. Then change the opening of the fresh air damper to 65%. The hot air temperature controller is tracking, so no issues there. However, the scrub reduced inlet temperature loop is unstable. Switch the simulator to hold. The scrub reduced inlet temperature controller is tuned with the fresh air damper on remote. On an increase in the fuel gas valve opening, the ratio control logic increases the opening of the fresh air damper. But with the fresh air damper on local, the fresh air damper opening and the fresh air flow are constant. With no additional fresh air to heat, the result is a larger increase in the scrub reduced inlet temperature. The sensitivity of the scrub reduced inlet temperature to fuel gas valve opening is higher when the fresh air damper is in local. Higher sensitivities can lead to stability issues in the scrub reduced inlet temperature controller. This explains behavior exhibited by the simulation. The opposite effect is also possible. That is, switching a final control element to local could cause another loop to respond so slowly that it effectively ceases to function. The next video explains the tracking required for a smooth transition from manual to automatic control.